Our first talk is by Lawrence, who's going to be quicker about things than I am. So it's a little pun on them. Take it away.
Hello. Hi, my name is Lawrence, and I'm here to present QUICKeR updates involving continuous key rotation. I did this work jointly with my co-authors Wei Go, Divya Agarwal, Amar Elabadi, and Trinab Gupta. Let's first start with an industry standard method of storing data in the cloud called envelope encryption. Envelope encryption is a two-level encryption scheme where a root key on a hardware security module encrypts a data key, and a data key encrypts a plaintext data. A client machine can securely store data in the cloud by generating a data key, encrypting the plaintext with the data key into a ciphertext, and communicating with the hardware security module to encrypt the data key with the root key into a wrap. Finally, the wrap and ciphertext are stored onto the database. To retrieve the data, the reverse operations can be performed. A client machine can download the wrap and ciphertext, communicate with the hardware security module to decrypt the wrap, and finally, decrypt the ciphertext with the data key. Unfortunately, cryptographic keys are vulnerable to key leakage in several ways. For instance, keys may be mishandled and inadvertently leaked, rogue employees may steal cryptographic data, buggy code may have vulnerabilities, malware can steal cryptographic keys, and more. One solution to this is via key rotation. Key rotation is the process of retiring old keys for new keys, which also necessitates updating ciphertext to be encrypted by new keys. Key rotation limits a ciphertext exposure time during key compromise and aims to provide post-compromise security, which means that corrupted old keys do not compromise the security of new ciphertexts. What's more, periodic key rotation is a required government standard and industry practice. Unfortunately, current solutions to key rotation are insufficient because they don't consider how key rotations may impact the performance and correctness of routine data retrieval and update operations. For instance, updatable encryption solutions do not consider concurrency violations in a practical system. Industry systems might only rotate the root key, which is insecure because it leaves the data key vulnerable. And conventional concurrency control system solutions are not optimized to handle an entire database update and may even violate post-compromise security. For instance, multi-version concurrency control may hold on to old ciphertexts. We present QUICKeR, a system which provides key rotations for both root and data keys. To avoid requiring system maintenance downtime, QUICKeR enables online key rotations and guarantees a stronger form of concurrency correctness called linearizability. Linearizability means that the operations can occur in any order and correctness is still guaranteed. Our solution proposes practical methods using both naive updates and updatable encryption with performance and security trade-offs between the two, and we provide experimental results to back up our system. QUICKeR adds trusted update machines, which one by one update all the ciphertext on a database and works concurrently with other client machines. In a round of key rotation, the HSM will have a new root key and old root key, and the update machine will update the ciphertext from the old to the new root key. Now that we have two keys, we'll want to guarantee that, one, clients know which root key to decrypt wraps with, because at any point in time, some ciphertexts are encrypted with the old root key and some with the new root key. And two, clients know which root key to update or insert new data with. We solve this by simply associating key IDs to each key in ciphertext and having the update machine communicate with clients in the database on the new root key ID. So client machines only encrypt with the new root key, and the database only accepts ciphertext encrypted by the new root key. To naively perform key rotation for a ciphertext, the update machine essentially decrypts the ciphertext and re-encrypts it with a new data key and new root key. The update machine first gets the old ciphertext and wrap, then communicates with the HSM to decrypt the wrap, generates a new data key, communicates with the HSM to encrypt the new data key with the new root key, generating the new wrap, decrypts the old ciphertext with the old root key, and then re-encrypts it with the new root key to generate a new ciphertext. And finally, the new ciphertext and wrap are put into the database. Unfortunately, this doesn't guarantee correctness because it occurs concurrently with other routine data update operations. Consider a situation where key rotation for a ciphertext begins and an update machine downloads the old ciphertext and wrap. In the meantime, a client machine is updating the data by putting a new ciphertext with new data in the database. When the key rotation finishes, it overwrites the client machine data with old information, which violates correctness. Traditional solutions to handling these concurrency problems, such as locking the entire key rotation operation or using transactional processing solutions, are either inefficient because they block or affect routine operations such as key rotation, or may have security flaws that no longer guarantee post-compromise security. Our solution is much simpler, more efficient, and guarantees linearizability, which means that no matter what order parts of operations are performed, correctness is still guaranteed. We accomplish this by associating ciphertext with a ciphertext version number, so that whenever the data is updated by a client machine, the new ciphertext is atomically put into the database, and the ciphertext version number is also incremented. Because before the key rotation of a ciphertext completes, the database atomically checks if the version number has not changed. And if it hasn't, then put the updated ciphertext, wrap, and key ID into the database. Otherwise, it aborts. Recall that we ensured that the new data is always encrypted with the new root key, so even under a key rotation abort, we do not need to update this ciphertext to new keys. And this is used to guarantee correctness for both the naive schemes and updatable encryption schemes. One problem with the naive solution is that it consumes high network bandwidth. This can be rectified with updatable encryption designed to enable in-place key rotations. Updatable encryption is an encryption system like any other with key generation, encryption, and decryption, but also adds two operations, token generation and update. The token generation function generates a token delta from the old and new keys, which is sent to the database to be used to run the update function to update the ciphertext from the old key to the new key. This guarantees post-compromise security with caveats that we defer to the paper. And additionally, there's a distinction between ciphertext dependent and independent schemes, which I'm omitting in this presentation. Using updatable encryption in QUICKeR, almost everything is the same as naive encryption key rotation, except that instead of downloading and uploading a full ciphertext, we use updatable encryption instead. First, we avoid downloading the ciphertext, only the wrap and version number instead. After generating a new data key and communicating with the HSM to decrypt and encrypt the old and new wraps, the client machine uses the old and new data keys to generate a token delta, which is used to update the ciphertext on the database. Note that we continue to rotate the root key naively because the wrap is small and inexpensive to encrypt and decrypt compared to the much larger ciphertext. Unfortunately, a conventional application of updatable encryption can still significantly impact routine operations performance-wise because the update function itself may still hold on to the database locks, slowing down other routine operations. In this example, the database is performing the ciphertext update function while holding on to locks, preventing other client get operations. Our solution is to simply shift the update operation onto a separate thread from the thread that accesses the database's data structures. This avoids blocking other client operations, and linearizability is still guaranteed from the earlier slides. Finally, we show some experimental results. We wanted to see how different performance bottlenecks on the database would affect the performance of naive updates and updatable encryption schemes, which we chose nested UAE, and how they perform under different locking strategies. A scheme performs better in these graphs if the number of key rotation operations, the x-axis, does not affect the performance of routine access operations, the y-axis. We expected that when the database is under CPU-constrained environment that naive updates would perform the best. However, the updatable encryption schemes performed slightly better because handling a high network load was surprisingly computationally expensive. When network bandwidth was low, the naive update scheme had a steep trade-off between key rotation operations and routine access operations. And finally, when neither CPU nor network bandwidth were bottlenecks, then locks became the bottleneck. And unsurprisingly, the schemes that hold on to the database locks the least perform the best. Note that in these experiments, correctness was not guaranteed because we were testing the effects of locking on the database. Lastly, we show in our end-to-end experiments how naive updates, single-threaded updatable encryption, and the multi-threaded updatable encryption schemes perform. Naive updates performs the best initially as it doesn't have to pay the cost of using updatable encryption. But at a very high key rotation throughput, the multi-threaded updatable encryption schemes impact routine access operations throughput the least. In conclusion, we propose QUICKeR, a system which provides online key rotations while minimizing its impact on routine operations. Our paper also shows a full proof of linearizability, discusses authentication, and compares the performance of different updatable encryption schemes based on security and performance. One limitation of our work is we did not assume a transactional processing system, and as we previously mentioned, some transactional processing systems have problems with compatibility, such as security, and future work can explore this direction. Thank you for listening to my presentation.
Any questions? And please wait for the mic if you have some.
On? Yeah, seems to be working. Didn't sound like it. Thanks for the talk. As someone who's more on the consensus and networking side, maybe this is a naive question, but do you make any assumptions about the communication models? Like, are all your messages eventually delivered, or can there be dropped messages? Is the communication synchronous, asynchronous?
That's a good question. I mean, I guess there is some implicit assumption that they like eventually arrive. Like it can't be like indefinitely long, but yeah, the messages can be received like out of order, for instance, and yeah, linearizability is still guaranteed.
Okay, good. Thank you.
So down here. Here. Go ahead.
Hi, thank you for the talk. I was just wondering, like, is the bottleneck for these key rotations more like you're updating the keys, or like the users are trying to update their ciphertext? Because it seems like you wouldn't be updating the keys that frequently.
Yeah, the best way I would describe it is that in terms of scalability for the system, as you know, as there's more and more data, you know, stored in the cloud, then you know, key rotation becomes more and more expensive. And so I would say that I would frame it in that way as the, you know, primary like bottleneck in a way. And so for that reason, we're exploring, you know, key rotation. And, you know, there are key rotation periods that are like standardized by, you know, like government, like for instance, NIST and whatnot, right?
Okay. Maybe if anybody has one last question while Sasha is setting up, there's one up there.
Did you handle a key supersession process? Did you handle a key supersession process, verifying old key with the new key can at the same time before transitioning?
I don't really follow, but I would probably say no.
Okay.
Seems to be some confusion there. Maybe talk offline.
Yeah.
Okay. So let's see if Sasha's all plugged in here. Oh, I'm sorry. Please thank the speaker.